So this week is about relativity, and we're doing special relativity, which is different to general relativity. Special relativity involves things moving at relative velocities that are constant. So in other words, you're observing a object moving at the distance at a constant speed. General relativity is more about gravity, and it does involve accelerating frames of reference. We don't really go into that because it's mathematically much more complicated. Looks like there's an awful lot of notes to learn, but really it's a case of getting your head around the key equations. They're not easy, partly because there's a lot of things that look the same. So, for example, T's and T naughts and U's and V's and V dashes and all sorts. If you can get your head around using the equations, then you've won 90% of the battle. So I'm just going to take you through the key elements of the summary page. But once you get your head around the first little bit, the rest of it does start to slot into place. So the first thing I just need to introduce you to is this equation here, which is gamma. It actually is the Lorentz transform. Now, effectively, this is a coefficient that tells us how much relativity is having an effect. At speeds that are very, very low, so, walking, running, trains, aeroplanes, this bracket here has a value which is very close to 0. So the whole value is quite close to 1, which means effectively relativity has very little impact. It's only when v starts getting up to a significant proportion of the speed of light that you'll start to notice a change. The two key changes you've got to be aware of are these two: time and length. So, in simple terms, a person observing an event that is moving in relation to them. So I don't know why we always use trains, but we do, so I'm sticking with it because it's traditional. There's a train moving at a certain velocity. This observer observes an event happen on that train that takes a certain amount of time. A second observer is standing on the train, sees the same event. So the idea is this event could be anything like a ball just falling from the ceiling to the floor, just to keep it nice and exciting. That happens in a certain amount of time. This observer in front in purple here, this one, we'll see that event take longer. Because the event is moving, time moves more slowly when it's been observed. We need an equation that will tell us what the time observed would be, and we refer to that as the relativistic time. Now, you might see some equations that have that as t dashed, but in the book you're studying from, it is just t. Now, gamma always has a value of at least 1 or more. T0 is the proper time. So that's the time that the person standing on the train, watching the ball fall to the floor, would see it happening. That's essentially the stationary time, the proper time, the time you would see, I suppose, what you might think of as the normal time. The purple person, the person standing on the platform out here, sees the train moving, sees the ball fall, and sees it take a different amount of time to hit the floor, as given by this equation here. The greater the velocity, the greater the value of gamma, so the longer they will see that happen. In other words, they see the ball fall in slow motion. What's interesting to note, but also a little bit mind-bending, is if the person on the platform also dropped a ball, and the person on the train watched the platform ball falling, they would also see that happen in slow motion. So each of these two observers will observe the other person moving in slow motion. And the simple reason for this is there's no way to tell which of the two objects is actually the one that's moving. From the point of view of the person on the train, the world could be rotating such that the platform moves backwards and the train is perfectly stationary. And for the person on the platform, it could just be the train that's moving. Neither of those situations is provably correct. If I were you, I'd pause the video at this point and get your head around that. Okay, the second thing that happens when you're watching an object move is what we call length contraction. Again, this depends on the gamma value, but this time we take the proper length, L0, which is the length an object would be if you measured it while you were stood next to it. In other words, while you're stationary. Divide that by gamma, and you get the relativistic length. So again, if we take the example of this train, if I was stood next to it, measured the length of the train, I'd get length L0. But if the train is moving at some relativistic velocity v, so close to the speed of light, and I'm stood on a platform watching the train go past, as it passed my tape measure that I'm standing holding, I would measure it being a lot shorter. That would be the relativistic length L. And again, you might see some books and some equations will reference this as L and L dashed as the relativistic length. But in your book, L is the relativistic length, L naught is the proper or original length. Just when you're doing questions on this, you should always notice that L is always going to be shorter than L naught. The object doesn't get longer, it's either its original length, or it gets shorter the faster it moves as it's being observed. Also important to notice that it doesn't change dimension another way. The object doesn't get smaller. If it goes fast enough, it doesn't turn into a toy train. It literally just gets shorter in the direction of travel. So as it gets faster, that's what happens. If it was to approach the speed of light, it would get infinitesimally thin. So it effectively would disappear. Again, at this point, I'd pause the video and try and get your head around that. It might be worth having a go at some questions just to do with time dilation and length contraction first. Once you get your head around that, the rest of this does start to make, well, a little bit more sense. Okay, there's a few applications to this. I'm actually going to come back to these two equations here because these two equations make a little bit more sense to begin with. So this is kinetic energy, relativistic energy, and we'll also look at relativistic momentum. Now, at one point it was correct to say that when an object moved, so our relativistic train, when you view it moving close to the speed of light, if it was possible to measure its mass, it'd be apparent that its mass would increase. But that's strictly not quite true, and it's not a real representation of what's going on. So the reality of this situation is the equation in 28.5. Hopefully you'll remember from last semester that momentum is mass times velocity. We have a relativistic momentum, which again involves the gamma function. And it is as simple as that. Gamma times mass times velocity. So the apparent momentum of an object would increase more than we would think it would classically when it starts to approach the speed of light. This also means that as you get close to the speed of light, your momentum can become infinite. And this is one of the limiting factors that stops an object from travelling at or beyond the speed of light. If you get close to it, you've got an almost infinite momentum. It would take an infinite amount of energy to accelerate you up to having an infinite momentum. So it's just not possible to achieve the speed of light as an object. You can get very close to it. Relativistic kinetic energies, well, the relativistic energy of an object would just be, in the same way that we used gamma m in the momentum equation, would be gamma m c squared. And the kinetic energy of that object is a little bit counterintuitively this equation here. Gamma minus 1 times mc squared. Now, we're all aware that E equals mc squared would be the equation that we're kind of seeing at the base of all this. So the equation for the total energy of something is just the relativistic increase in energy as a result of this increase in mass or momentum. The kinetic energy equation, if at first glance, looks like it's missing a velocity. Remember, kinetic energy is a half mv squared, and yet we're saying this is half mc squared. But do remember, it's got the gamma function there, and gamma, don't forget, does contain a reference to velocity. You can actually derive this from the original equation, although there's no requirement to do it, but you will see where it comes from if you do go through that process. So there's a couple of equations extra at the bottom, which you'll make sense of when you read through that. The total amount of energy, again, these aren't really complicated to understand. It's just a case of knowing what all the terms mean and being able to put numbers in the equation. Okay, so let's just go back to two of the more complicated equations that you've got to make sense of. The first one I'm going to look at is the Doppler effect equation. So Doppler effect is, as you'll know, down to the relative motion between two objects. So if you've got an object like an ambulance and it's emitting a siren, but it's moving quite fast towards you. The waves in that direction become squashed, and what an observer in front of the ambulance hears is something a bit more high-pitched, and behind, the waves become stretched out, so an observer behind the ambulance hears something that's lower-pitched. The same is true for light. An object that moves in one direction and emits light in front of it, that becomes a shorter wavelength, would become bluer, or what we call blue shifted. And equally behind it, it becomes stretched and becomes redder if it's a colour, which we refer to as being red shifted. Just note that this doesn't necessarily mean that something becomes blue or becomes red. It just moves in that direction. But in actual fact, you could move beyond those colours. So you could become so red shifted you turn into infrared and actually become invisible. You have to be going very fast to do it, though. So this equation, again, just involves the velocities of the relative objects, the original wavelength, which would be observed in a lab, and then the observed wavelength, lambda OBS, which is what you would actually observe as a result of that relative motion. So that is the shifted wavelength. If you're studying astrophysics and cosmology, the idea of the Doppler effect is something that will become quite important, but it isn't just a cosmology concept. It is something that's used in physics. For example, it is how speed cameras work. So the final equation, which is probably the trickiest, is this one here. Okay, so the problem we've got is no object is allowed to move at or close or beyond the speed of light. So if we take an object like our magical train, and let's say it's travelling at 90% the speed of light, 0.9 c, and somebody inside that train fires something forwards, and they fire it forwards at 0.5 c, half the speed of light. So it's travelling 0.5 c faster than the train is. Now, an observer on the platform watching all this going on, while being very astounded, would also probably classically think that this object would be moving at, well, 0.9 plus 0.5 c, so 1.4 c, nearly 1.5 times the speed of light. That is not allowed. So we can't just add velocities like we would classically. We have to have an equation, which is the one you can see in the red box. Now, you don't even need to go into the chapter to be able to see what all the bits of this mean, because it explains it pretty well in the glossary. But if you do go into the chapter, it does give some examples of how to use it. What we're effectively saying is that we've got the velocity v, which would, in this example, be the velocity of the train. So velocity v is the relative velocity between the two observers. So in this example, the train and the person on the platform. The train is going at velocity v relative to the person. U and u dashed are the two observed velocities for the third object. So the train and the person on the platform are our observers. This, I don't know why it would be a torpedo, but let's go with a torpedo. This firework, this rocket, whatever it might be, has been fired forwards. The train would view this as travelling at one velocity. The person on the platform would view this as travelling at a different velocity. So the u and the u dashed are the velocity of this object, dependent upon which observer you are referring to. So this equation, as it stands, u equals v plus u dashed, and so on, would give the velocity of the firework being fired from the train according to the person on the platform. So again, it's worthwhile just getting your head around a couple of examples in the book, but once you do, you realise it is just a case of identifying the variables and putting the right numbers into the equation. Actually, although it looks nastier, those are less tricky than figuring out some of the time dilation questions that you'll meet on the web work.